So this is a data analysis part. So because I've already done the experiment, so now let's look at the data. So this is angular velocity, and also this is time. So angular velocity with respect to time, I can get the angular acceleration. So just by look at these values, so this m values is 2.162. So that should be angular acceleration, which is equal to rate of change of angular velocity. So I've done multiple experiments already. So let's look at the second data. So the second data. So I have the second data already. So now, so this is the second set of data, which is 2.184 radian per second square. So this is the data. So I write down the first angular acceleration, the second angular acceleration. For this quick demo, I calculate the average acceleration should equals 2.178 radian per second square. So that is the angular acceleration measured with the sensor. And also, now let's look at this part. Because I can measure the weight of this mass, which is roughly 50, I think that is 50 gram. So in this case, because a few seconds ago, I measured 50.3 gram. So that's mg, which is weight of this mass, times the radius of the pulley. So this is already measured, which is 2.7 centimeter. I calculate the torque provided by the mass, which is 0.0133 Newton meter. So next, let's plug in the angular acceleration. I can get the experimental moment inertia should equals to 6.17 times 10 to the negative 3 kilogram meter squared. So this is the experimental values of moment inertia. In this case, we have a rotating rod with a mass attached to one end of the rod. So now, next, we move on to the theoretical. So first of all, I can measure the mass of this mass. I put it, okay, so let's 0. So let's measure the mass. So which is 80.3 gram. So I already put this number here, 80.5, 80.3. So 50.3 is the mass of the weight. So I can measure the distance from the center of this mass to the center of the rod, which I already did. Okay, let me rotate this a little bit. Okay, so I already measured these values. I put this value as 18.0 centimeter. So I have uncertainty of 0.2 centimeter because I'm not exactly sure where the center of the mass is. So I can calculate the moment inertia of the mass. So this is a load mass times r squared, because I have two mass attached to the rod. So the moment inertia is 5.22 times 10 to the negative 3 kilogram meter squared. Well, if you look at these two values are actually very different. They have difference of, I think, at least 1, right? So because in this case, we have a rotating metal rod with a mass attached to it, which means that we have not taken the moment inertia of the metal rod into consideration. So next, I calculate the moment inertia of the rod, which is 1/12 mass times r squared. So the mass of the metal rod is 40.7 gram times the length of the rod. So I already measured. I get these values. So I add these two moment inertia together, I get 5.71 kilogram meter squared. Now, this value is very close to the experimental values. Now, finally, the difference of these two values is 8.1%. So the experimental value should equals to 6.17, and the theoretical value should be 5.71 kilogram meter squared. We can identify certain areas in this experiment. For example, we have not considered the friction force. So friction force might provide a torque.